Hey everybody, Dr. A here, and in this video we're going to be providing some background information on wind loads, and we're going to be referencing the semi-recently released ASCE 722 document. So let's go ahead and get started. So before we dig into each of these line items here, I like to preface this with wind loads, especially when you're first learning about them and you don't know much about them, can be quite challenging and it can be quite confusing when you've never dealt with it before. So in this particular video, I'm going to do my best to outline the basic information that you need to navigate a wind load analysis. And we're not going to go into all the details of any kind of numerical example, but just basically how to navigate this ASCE 722 reference. Now, if you're still looking at ASCE 716, it'll be a very similar kind of layout. In fact, the chapters are pretty much the same type of information in the chapters with some moderate updates in a few of the chapters. But let's go ahead and get started. In our checklist here that we already have written down, the wind loads, when you're looking at ASCE 722, the wind load information is found in chapters 26 through 31. So if you have your ASCE 722 handy, it might be a good idea to get the provisions book out and open that up and follow along with me, okay? So the first chapter that we encounter a lot of important information regarding wind loads is in chapter 26. Chapter 26 is several pages long. It gives a lot of definitions at the beginning of chapter 26. There's also some basic wind speed maps in chapter 26 that you end up having to use quite often. And then there's several governing equations and tables and figures in chapter 26 that no matter what later wind load procedure you end up using, you're going to have to go back and utilize stuff from chapter 26. So that's a really important chapter, okay? The next chapter that gets into a little bit more of a specific procedure is chapter 27. Chapter 27 covers what's called the directional procedure for the main wind force resisting system, okay? Now, we often abbreviate the main wind force resisting system as MWFRS, okay? Now, when we think of a main wind force resisting system, we're thinking of maybe the framing elements and maybe the beams and the columns that are the main structural system that is holding up our structure and resisting those wind loads, all right? So chapter 27 covers what's called the directional procedure. Now, when we go into chapter 28, which is the next chapter involving wind loads, that's going to cover what's called the envelope procedure, okay? Now, this is a different kind of procedure than the directional procedure. They each have their own set of assumptions of when each of these procedures is appropriate to use for a given structure and when each one is maybe not appropriate to use for a particular kind of structure. So when you dig into each one of these on your own, not in this video, you need to look at the first page of both chapter 27 and 28 and see, is this procedure applicable for what you are dealing with, okay? Now, when we get to chapter 29, this is a different kind of directional procedure. So the underlying theory behind what happens in 29 is very similar to what's happening in 28, except this directional procedure that's summarized in chapter 29 is for building appurtenances and other structures, okay? Now, what do we mean by building appurtenances and other structures? Well, these are things that might not be the main wind force resisting system of your actual structure. These are items that are like attachments to your building, or maybe you have a small sign or tank that is either freestanding or on the rooftop of your actual building itself. So that's what we mean by building appurtenances and other structures. Now, when we get to chapter 30 deals with components and cladding, okay? So this is the chapter that we use whenever we want to calculate the wind loads acting on a component or a cladding of a building. Now, what's a component or a cladding? Well, we're going to get to that later in this video, but in general, cladding is the actual exterior surface of your building that the wind is directly coming in contact with. So that would be like a window or a door or a wall. That's the part of the exterior of your building that the wind is actually blowing on, okay? That's what cladding is. Now, what is a component? A component is the first type of element that wind load is transferred to from the cladding. So components, for example, are things like purlins or girts, or sometimes even roof trusses would be considered a component. Nevertheless, components and cladding are not your main wind force resisting system. Now, whenever the load transfers from the component, where does it go to next? The next place it goes is your main wind force resisting system. So I'm going to draw a diagram that shows this a little bit more clearly later in this video. Chapter 31 is a more of a research type of procedure. This is called the wind tunnel procedure. So wind tunnel procedure is typically used whenever you have a specialty project and you need to have either a model or a prototype that's inserted into an actual wind tunnel in a laboratory setting. Okay, so this is used more for very, very specialized structures and projects. And then I put in red here tornado loads. So tornado loads are very similar to wind loads, but they are a little bit different, which is why I wrote it in a red color here. But Chapter 32 of ASCE 722 discusses how to handle those extreme wind events that we call tornadoes, okay? So let's go ahead and go into a little bit more detail on Chapter 26. So a lot of what we're going to talk about in the rest of this video kind of ties back into the general information of Chapter 26. And again, Chapter 26 is super important because all of these other chapters, 27 through 31, especially 27 through 30, tie back in to the general information that is in Chapter 26. So we really need to get comfortable with Chapter 26. All right, so let's go ahead and start with some basic vocabulary. Basic vocab. And again, I'm mostly going to be referencing things that we see or are found in Chapter 26. So if you have that ASCE 722 with you, go ahead and open up to Chapter 26. So to get started with some basic vocabulary, I'm going to go ahead and I'm going to sketch out a 2D section view of a structure, of a building, okay? So let me make this drawing look a little bit nicer. All right, so let's say we have a 2D section view right now. All right, so if you want to say it out loud where anybody around you can hear you, what is the name of this roof? What is this roof called right here? Well, I'm going to tell you the answer in 2 seconds. This roof is called a gable roof. So that's a fun little vocabulary word if you hopefully remember that. Gable, G-A-B-L-E, gable roof. So let's look at this 2D cross-section view of a gable roof structure. And let's say that the wind is blowing from this direction, all right? Now, the surface of the building that the wind is directly hitting, okay, you're going to generate this wind pressure on this surface, okay? This is called the windward surface, okay? Now, what about on the opposite side of the building, okay? On this side of the building, where it's the opposite side of the building that the wind is blowing on, this is what we're going to call the leeward surface. Now, it's important to note the direction of these vectors, okay? On the windward surface here, on the windward wall, this wall is experiencing a compressive type of pressure, okay? Now, when we go to the other side of the building, the leeward surface, let's label this leeward surface. The leeward surface is experiencing what we call suction, okay? Now, the reason this happens is because as the wind hits this windward surface, it eventually blows around the building. This is my poor attempt to show the wind blowing around the building, okay? And when it blows around the building, it's going to create a suction effect on the opposite side, okay? Now, what's going to happen to the roof is the next question. Let me erase these little squiggly arrows here. What happens on the roof? Well, depending on the slope of the roof, you are going to develop either a compressive or a suction pressure effect on the roof surface. So to illustrate that, I'm going to draw my pressure vectors going in both directions. It could either be suction or compression on the roof. Now, what will influence that? Well, what influences that is in large part going to be the roof slope angle. So I'm going to label this roof slope angle theta right here. Okay, so if theta is very small or very large, that will impact if the roof panels are experiencing either compression or suction. Okay, another important vocabulary word, let's change color here, is this peak line right here. Okay, at the very peak of a gable roof, you have what's called the ridge, okay? And this is running longitudinally. So in this video, the ridge is like coming in and out of the screen at you, all right? All right, what else is important here? Well, if you noticed, the roof is overhanging just a little bit on either side. If you notice, I drew a little part of the roof that's overhanging off of the wall, okay? That little overhang is often called the eave, okay? So the dimension or the vertical measurement from the ground surface to the eave here is called the eave height, and we typically call that H sub E. So eave height, okay? Another important height we need to note is what's called the mean roof height, okay? So I'm going to draw a dimension line from the center of the sloped roof, and that's going to be a vertical dimension as well. That's just called H. This is called the mean roof height. Okay, now what is the mean roof height? Well, it's the height halfway in between the eave height, which is right here, and the ridge height, which is up here. Okay, now the mean roof height is really important because that's a measurement that we end up using a lot in a lot of these wind pressure calculations that we're going to talk about later on. Okay, and the last vocabulary word I'm going to talk about right now in this figure is what we call the base shear. Okay, so I'm going to put down here at the bottom of the building a vector here, a single vector. I'm going to call this capital V, all right? And this is going to be called the base shear force. And I'll give you a better definition of this later on in this video. But in general, this is a shear force, and it's a force, not a pressure, that is going to be at the base of your structure. And it is a response to the wind pressures on the windward surface and the leeward surface, okay? And so what you end up doing is you calculate these wind pressures on the windward and leeward surface, and you calculate them as a force, so you multiply that pressure by the area of their respective walls, the windward wall and the leeward wall, and the area is, of course, coming out of the screen at you, and you add all of those zones up, and you get the base shear force, okay? So anybody who's already learned a little bit about earthquake loads, you might have learned something called the base shear force when you're talking about earthquake loads. Well, it's a very similar idea with wind loads, okay? And it's something that we are interested in with wind loads, and we're also interested in it with earthquake loads, okay? So let's keep going with some more important terminology. One of the things that you have to identify early on whenever you're doing your wind load analysis is what's called the risk category. Okay, now the risk category is really defined in ASCE 722 in section 1.5.1 and table 1.5-1. So risk category is not just a wind load vocabulary term. It's a term that's used in general regarding any kind of building or structure, okay? But we utilize it in wind load analysis. So what is a risk category? Well, there are 4 of them, okay? We have, I'm going to abbreviate this RC. We have risk category 1 through 4, okay? So basically, depending on how critical your facility is to human life, you're going to categorize your building as either risk category 1, 2, 3, or 4. RC1 structures, so I'm going to say RC1 structures have a low risk to human life if failure occurs, okay? I'm going to skip all the way down here. I'm going to leave a big space here. I'm going to jump to RC4. Risk category 4 is the opposite end of that spectrum. Risk category 4 are what are called essential facilities and facilities that pose a very significant risk to human life if failure occurs. So what are some examples of risk category 4 structures? Well, essential facilities would be like hospitals, fire stations, police stations, okay? These are facilities that you want to remain functional during a natural disaster, okay? Now, risk category 4 also includes facilities that, may pose very significant risks to human life if failure occurs for other reasons. So, for example, if you have a warehouse in a downtown of a city that's housing flammable chemicals, right, or a lot of combustible materials, and so if the structure itself fails, those chemicals could, pose a risk to nearby human life. That would be an RC4, a risk category 4 facility as well, okay? Now, what about RC2 and 3? I'm I'm skipping around a little bit. I'm gonna cover RC3 next, okay? RC3 are facilities that pose some kind of substantial risk to human life if failure occurs, okay? So I'm gonna note here, failure causes substantial risk to human life, okay? So these are facilities that might not be as critical as RC4 facilities, but they're pretty important, okay? Now, I'm going to jump to RC2, so save RC2 for last. RC2 are facilities that are not in RC1, 3, or 4. So I'll tell you this, most structures are RC2, okay? A lot of structures are considered RC2, okay? RC3 and RC4 structures are all over the place as well, but most structures are RC2, okay? RC1 structures would be something like if you have an abandoned warehouse that's housing just a bunch of old farming equipment out in the middle of nowhere, right? That would be an RC1. If that structure fails, then that's not really going to pose a risk to human life, okay? So those are our risk categories, okay? Another important vocabulary word is called the basic wind speed, all right? So let's write this down, basic wind speed. And we abbreviate that with the letter V, capital V. Now, where do we get this? This comes from ASCE 722, and we can get this from figures 26.5-1, and there's a set of those. There's several of these. They're maps, but we get these basic wind speeds, and these are based on risk category that we just talked about. So if you have a copy of ASCE 722, I would go ahead and open it up, and I would take a look at figure 26.5-1, and you see that there are several of these maps there, okay? And they're further categorized as 26.5-1A, B, C, and D. Now, those different maps, if you read the bottom of the pages, they're going to be categorized in risk category 1, 2, 3, and 4, okay? Now, the basic wind speed, which is V, it's got units of miles per hour, and then it also has a metric equivalent in parentheses there in meters per second. So if you need the metric units there, they're in parentheses next to the value in miles per hour directly in those maps, all right? The next important definition of vocabulary we're going to talk about is what's called the surface roughness category. Okay, so let's write that down. Surface roughness categories. Okay, and again, if you're referencing ASCE 722, this is going to be section 26.7.2. All right. Now, there are 3 surface roughness categories that we're going to be interested in. Okay, that's going to be surface roughness category B, C, and D. Okay, so if we're looking together at our ASCE 722, I'm going to say SRB, surface roughness category B. That's going to be urban and suburban areas, okay? Now, typically this is also terrain with closely spaced obstructions. All right, so when you're thinking about a downtown of a city, that would likely be surface roughness B, okay? What about surface roughness C, okay? These are areas with open terrain with scattered obstructions. For example, open grasslands. Okay, and then surface roughness D, so SRD, that's going to be flat, unobstructed areas and water surfaces. Now, ASCE 722, if you're looking on that page with me, they provide a little bit more details in these definitions, but this is a quick summary of it. Now, depending on your surface roughness category, you then move on to determining what's called the exposure category. So I'm going to scroll down a little bit, and we're going to write exposure category here, all right? Exposure category, okay? Now, this is referencing ASCE 722, and we're in section 26.7.3, so it's pretty much on the same page or next page from the surface roughness category, okay? And again, this is based on the surface roughness and other terrain information, okay? Now, we have exposure categories B, C, and D, okay? Now, the exposure categories and the surface roughness categories are almost directly connected together, but not quite, okay? So surface roughness B is almost directly connected with exposure category B. Surface roughness D is almost directly connected with exposure category D, but the exposure categories do have a few more stipulations in there that I'm not going to go into the details with in this video. But if you got your ASCE 722, you need to be reading along, and you can pause the video and kind of dissect that a little bit more on your own. All right, now let's get to some of the governing formulas. All right, so one of the first things that you're going to have to calculate whenever you're doing a wind load analysis is what's called the velocity pressure, okay? And we call that Q sub Z, all right? So we're going to say this is the velocity pressure, Q sub Z, and we're going to say it's calculated at a height Z on a structure. Now, even though the name is velocity pressure, it is a pressure. You're calculating something that's going to pop out units in PSF. Now, I'm going to go ahead and say it now, and I'm probably going to say it several more times in this video. Typically, when you're doing a wind load analysis, the velocity pressure calculation is one of the first calculations, and it is an intermediate calculation, which means that typically you do not calculate the velocity pressure just for the sake of it. Typically, you calculate the velocity pressure and then you use it to calculate other things later on, okay? But all of these later calculations are directly tied back to the velocity pressure, which is why it's so important. And so how do we calculate this? Well, the velocity pressure, Q sub Z, is calculated as 0.00256 kz, kzt, ke v squared. And this is going to pop out units in PSF, okay? Now, this V right here is that basic wind speed that we talked about a few minutes ago, right? This is the basic wind speed in miles per hour that we get from the maps in chapter 26, okay? Now, this equation, you might look at this and you might say, well, hey, wait a second, how do I take miles per hour and then I square it and I punch it through this equation and I get units of PSF? Well, this is a semi-empirical equation, okay? And in fact, this coefficient here, 0.00256, is based on several factors, and it's related to the density of the air as well, okay? So when you insert the basic wind speed in miles per hour here, and don't forget it's squared in this formula, and you insert these other coefficients here, you will end up popping out this value of QZ in PSF, all right? Now let's talk about these other factors here, okay? So KZ, which is this first value here, the first coefficient here, is called the velocity pressure exposure coefficient. And in ASCE 722, we're going to get this from table 26.10-1. So go ahead and maybe follow along with me and find that table 26.10-1. And if you look at that table, it's going to be based on exposure category, okay? So if you notice, there's several columns there, and it's based on exposure category and height, all right? So what you do is you find the height that you're interested in. That's the left couple of columns. You can do it in feet or meters. And then you also need to know the exposure category you're dealing with. Is it B, C, or D? And then you can extract the KZ value that you're interested in. Now, if you want the governing equations of how to calculate KZ from an equation perspective, that's going to be just below table 26.10-1. So you see there's a little bitty table with several different KZ equations below below the table 26.10-1 that you can calculate KZ directly, but it's usually preferred and quicker just to extract values from the table 26.10-1, and you can use linear interpolation in there as well. In fact, there's a note below table 26.10-1, note number 3, that says linear interpolation for intermediate values is acceptable. Okay, so that's KZ. What about KZT? That's our next coefficient there, KZT. So this is what's called the topographic factor, okay? And we're going to get this from ASCE 722 from figure 26.8-1, okay? This can be quite a little bit of a lengthy process to calculate KZT, so I'm not going to go into that in this video. But KZT is a calculatable value, okay, based on the topography of the land that your structure is on. Now, for buildings on flat ground, KZT is going to be equal to 1. So I'm going to say for buildings on flat ground. Now, if you have a little bit more specific information of the topography of your site, you can enter into figure 26.8-1 and you can calculate KZT. But again, I'm not going to go into all those details in this particular video. Okay, what about KE? KE is called the ground elevation factor, okay? And from ASCE 722, this is going to be table 26.1-1. So if you look at that table, 26.9-1. Let me correct that. 26.9-1. You see that the ground elevation factor is based on the elevation of your site above sea level. Okay, now there's a note there. It's a note right below the table, and it's also right above the table. It says you can take KE as 1 to be conservative. Okay. And if you look at that table, what you see is as you get farther above, as your ground elevation is farther above sea level, KE gets smaller and smaller. So you can extract a KE value if you know what your ground elevation is, but you can always take it. The code, ASCE 722 always permits you to take it as 1 to be on the conservative side. Okay. So that defines this velocity pressure and how we calculate it. And again, I've said it already. This is a really important value. It is a pressure in PSF, but typically you don't stop there. You're using this QZ value to perform other calculations that are related to those different chapters we talked about at the beginning of this video, chapters 27 through 30 in particular, okay? Let's keep talking about some other important definitions, okay? A lot of our methods that we deal with in wind load analysis have to do with how tall the building is. In particular, a lot of things either simplify or have their own set of rules if you have a low-rise structure. So I like to define what does it mean to be a low-rise structure. So a low-rise structure is one that has a roof mean height, which we talked about that earlier, that's little h, has a roof mean height less than or equal to 60 feet. And your mean roof height is less than or equal to the minimum plan dimension, okay? So what does that mean? That means that if I draw a little sketch here of my building, okay? Here's my mean roof height. This is h, and it's going to be less than or equal to 60 feet, and this is an elevation view. If I look at a plan view, okay, if I look at a plan view and I call this dimension L and I call this dimension B, Okay, a low-rise building is also one in which H is less than or equal to the minimum of L and B. Okay, and so if you satisfy both of these little criteria, your building is what is called low rise. And again, once you start going into these very specific methods, chapter 27, 28, 29, 30, there's a lot of definitions that say, hey, if you have a low-rise building, do this. And so that's why it's important to really understand what does it mean to be low-rise, okay? Another definition, and this one is one that we talked about briefly earlier, and that's components and cladding, okay, which we abbreviate C and C, okay? So these are elements of the building envelope or elements of appurtenances that are not part of the main wind force resisting system. Okay, so what does that mean? So here's what I'm going to do. I'm going to draw another figure, and it's going to be a kind of a partial section through a building. So let's say that here's a roof here, and here's a wall. Okay, and this is just kind of a partial section through. Okay, now the wall and the roof would be examples of cladding. Okay, so examples of cladding would be windows, walls, roof sheathing. Okay, ... I'm going to say anything that directly receives wind load. Okay, and I think we said that earlier at the beginning of this video. Okay, now that's cladding. What about components? All right, components basically receive the wind load from the cladding. All right, and so examples of these are like purlins and girts. Okay, so what's a purlin and what's a girt? So we'll draw that here on our little figure. Okay, let's say that you have these little members here on the wall, and I'm going to make them little eye-shaped members. Okay, these little guys are called girts. Okay, so they're like little beams, and they're connected to the wall, okay? And they're running longitudinally in and out of the screen at you, and they're like little beams that are that are indirectly absorbing the wind load. The wind load is being directly applied to the wall here, okay? So here's that wind pressure from the outside. And then this wind pressure gets transferred to these little beams here that we call girts, okay? And in a similar way, something similar can happen on the roof system. We can have little eye-shaped members here that are like beams that are called purlins, okay? And the purlins are a component that receive the load that is transferred from the wind load that's applied to the roof sheathing, that cladding. Okay, so we're going to make a little label these as purlins. So they're like little flexure members, like little beams, similar to girts. Okay. Now, what about the main wind force resisting system? That's the important thing, right? That we end up really caring a lot about. So the main wind force resisting system is a larger scale structural system that the loads are transferred to next, and then ultimately down to the foundation. So for example, the main wind force resisting system could be a frame here. So let's draw this frame here. And this frame could be wood, it could be steel, it could be anything. Let's say that this is a two-member frame, and let's say that, you know, maybe it's some kind of wood frame and we have some kind of strap connection here with some nailing or some bolts in there. So this right here in green is a frame, and that's the main wind force resisting system. So one more time, the wind is acting on cladding, which is the exterior surfaces of your building, and that load is transferred to components, which are connected to the exterior surfaces, but they're just on the interior. So examples of that are like girts and purlins, okay? Then that load is transferred to your main wind force resisting system, which is typically could be a truss system, could be a more complicated beam system, column system, or in my diagram here, it's a frame, okay? So that's most of the vocabulary. The last couple things I want to point out, and then we're going to be kind of wrapping up this video. It's kind of a long video. We have something called the design wind pressure, and we call that little p, okay? So this is the design wind pressure. Now, what does this depend on? Well, it's based on that Q sub Z calculation we talked about earlier. It's based on the velocity pressure that we calculate in chapter 26. Now, it's also based on, so we're going to say, and the details of chapters 27 through 30. So depending on what specific structural scenario you're dealing with, you're going to then enter into chapter 27, 28, 29, 30, so on, and you're going to use that QZ that you calculated from chapter 26, and then you're going to utilize that to calculate a design wind pressure. And depending on what your what your structure is, your design wind pressure is going to be a function of other details from one or more of these chapters, okay? And then the last thing I want to kind of redefine, I defined it briefly earlier, is that base shear, okay? So this is the base shear force, and it's computed based on external design wind pressures. So it's based on external design wind pressures, P right here. Okay, so again, this video was meant to give you kind of an overview of a lot of very critical definitions, vocabulary, and a lot of important information from chapter 26, which is kind of the anchor chapter of all of wind load calculations. So I hope you enjoyed this video. If you found this helpful, please hit like and subscribe, and be on the lookout for other videos similar to this. Thanks for watching.